கேக்குதா சார்?
எஸ் சார்.
ஓகே. Shall we start, sir? Yeah.
Yes, sir.
Okay, sir.
Okay. Good evening, student. Namaskaram. Today, 11th physics first class. Today topic is work energy power. In that unit, we have to study law of conservation of energy. Okay. So in this class, we are going to talk about one of the most important laws in all of science. That is law of conservation of energy. Okay. So let's just start with that one definition. I will share. Okay. So this is the definition for law of conservation of energy. That is, the total energy of an isolated system is constant. Energy is neither created nor destroyed. So you can create some energy or destroy that energy. Okay. It could only be transformed from one form to another. Okay. This is the definition for the law of conservation of energy. Okay. It's clear. Okay. First of all, now we have to understand this. What are the types of energy we have already studied? That is, only two types of energy we can discuss here. Okay. First one, that is kinetic energy. You might see. Okay. What is mean by kinetic energy? Which is the energy due to object motion. Energy due to object's motion. Clear? Which is a energy due to an object motion. Formula for that kinetic energy, Ke, I have put Ke, kinetic energy, which is equal to half mb square. Yes. Here, m be the mass of that object. B be the velocity of the object. Velocity, or you can say speed. Okay. Whatever else. Speed is a scalar quantity. Velocity is a vector quantity. Okay. So half mv square. Mass, velocity. Mass into velocity, which is gives kinetic energy. Mass in kilogram, and as well as velocity. Already you know that units ms power minus 1. Okay, these are the units. Okay, so here we can infer that velocity is directly proportional to kinetic energy. Yes, then faster you go, you have more kinetic energy. Okay, faster you go, you have more kinetic energy, and the slower you go, you have less kinetic energy. Okay, it is clear. This is a kinetic energy. We have study about already in a previous class, that is potential energy. Yes, that is a second type of energy here, potential energy. This is the energy due to object position. Okay, object's position. Kinetic energy due to object motion. Potential energy due to object position. Okay, so let me put PE, that is potential energy. Already you may know that formula for potential energy, that is mgh. Correct? M, mass of that object. G, Acceleration due to gravity, h. H be the height of that object from the earth surface. Yeah, okay. So here also you can infer that the mass is directly proportional to potential energy, and the acceleration due to gravity is directly proportional to potential energy. And as well as finally one important quantity is there, that is height. Height also directly proportional to potential energy. So we can understand it a little bit deeper later. Okay, so this is a basic. Then in the case of mechanical energy, you were to combine these two type of energy. Okay, in the case of mechanical energy, you have to combine these two type of energy. That is a mechanical energy. Mechanical energy, which is equal to kinetic energy plus potential energy. Okay, this is the total mechanical energy. Okay, this is a law of conservation of energy. Mechanical energy, which is equal to kinetic energy and potential energy. And you may think that is only these two type of energy as the only universe. Not. Okay, there are other types of energy, maybe thermal energy, nuclear energy, chemical energy, but these are not the only forms. That is kinetic energy, potential energy, only forms. So when we talk about the law of conservation energy, things like kinetic energy could be transformed into some other energy, some other form of energy, that is chemical energy, potential energy. Okay. So here we are not going talk about those other type of energy like chemical energy, nuclear energy. Okay. Okay. So in this class, first think about how mechanical energy can be conserved. Okay. Okay. So first of all, I have drawn Earth here. Okay. It is a kind of flat surface. And then let me draw one ball is there. Okay. So let's say my ball is held about the earth here, just like that. So while the ball is stationary, we will assume that there is no air here. Okay. We can consider here, there is no air here. Okay. While the ball is stationary like that, then we have say that it has all potential energy. That is, we would call it gravitational potential energy. Okay, GPE, gravitational potential energy. So it is a symbol in your book U. Okay, we could say there is a gravitational potential energy U, and we could say that there is no kinetic energy here. No kinetic energy here. Only one type of energy is there. That object has only one type of energy, that is potential energy in the above surface. Okay, above the earth surface. No kinetic energy. Okay, but what would happen if I were let go of the ball? Think about it. It will come to here, come to this place and hits the ground. But we can consider that is it is not bounce back. Okay, only sit there. Once hits the earth surface, it is not bound back, only sit there. Okay, clear? Well, in that situation, all of a sudden gravitational potential energy is converted into some other energy. Okay, so potential energy converted into some form of energy, kinetic energy or thermal energy. Okay, once it touches that ground, it is not stationary. Okay, here stationary, and in that middle it is moving. Okay, it is moving. Once hits the ground or surface, earth surface, it have no gravitational potential energy because there is no height. Okay, so in this case, it's going to have lot of kinetic energy. So here only kinetic energy, no potential energy. Okay, in that surface. So what we saw here, that is potential energy all gets transformed into kinetic energy, right? Once a ball touches the ground. Now you may think that where is that go, that energy type of like potential energy, where that energy goes? Because that energy only converted into kinetic energy. Okay, you cannot destroy some energy or create some energy. You can only transform one form to potential energy to thermal, or potential energy to kinetic, whatever. So kinetic energy to potential energy, kinetic energy to thermal energy. Okay, we can see one simulation later. In that simulation, you can understand better. Okay, so this is a law of conservation energy. Once hit the surface, maybe some form of heat here. Okay, maybe you can touches the ball and you feel that some heat or ground, because that thermal energy is converted from potential energy or some other energy or kinetic energy. Okay, so the ball and the ground would actually get a little much warmer, because that kinetic energy touches the ground, convert into thermal energy, or potential energy convert into thermal energy. Okay, right. Okay, in that case, we have considered no air is there. Suppose one student may think about that. What is the case of if some air is present? Okay, some air molecules present. So in that case, this is a air molecules. Okay, so once a ball falls down, it goes through the air. You could consider that air resistance. Okay, this is the air resistance. That is air friction. Also, we can call the air friction. That friction slow that ball down. Okay, yes, slow that ball down. So maybe it would not have as much kinetic energy when it gets down here, but it feels or it exerted by the some additional restriction, that is air friction. Okay, so think about it. Some form of resistance is there. So some form of energy is there, that is thermal energy. Because once you resist something, you can touch that thing, you can feel some warmer, because of that energy is converted to heat energy. You can see in the electronic devices. Yes. Okay. So initial kinetic energy, initial potential energy, and I can combine these two type of energy, which is equal to final kinetic energy plus final potential energy. Okay, because energy is not destroyed, has not been destroyed. As the ball falls down, it's going to heat up the ball and the air around it. And so once again, the air resistance, that is a dissipative force. We are not going into the topic of dissipative force, only isolated condition, isolated system. So only we can consider only two type of energy, kinetic energy, potential energy. There is no air restriction, air friction. So in that case, conservation of mechanical energy or conservation of energy, which is nothing but initial kinetic energy plus initial potential energy, which is equal to final kinetic energy plus final potential energy. Okay, clear? In your book, you can see that definition for conservation of energy. We can calculate. Okay, now this is a ground level. You take up ball here, that position A, and ball touches the ground, and this is labeled as C. In the middle way, I can take one position, that is B. Okay. From the ground level to that A position, there is a height, that is H. And the distance between A to B is X. The distance between A to B is X. So the distance between B to C, H minus X. H minus X is there. Okay. This is the distance between B and C. So in that position, ball is already, I told you, the ball is stationary. So there is no movement. So there is no velocity. There is no initial velocity. So I can put U is equal to 0. That is U means initial velocity. Okay. Ball falls down here from the top to bottom. So here. So A acceleration of the object, which is equal to plus G. Because if one ball moving opposite to the acceleration due to gravity, we can put A is equal to minus G. But in that case, a ball is comes down due to acceleration due to gravity only. So A is equal to plus G. Plus minus is the symbol for direction, one opposite or along the direction. Okay. Right. Consider a freely falling body. Here, it has mass m. That object has mass m. Released from a point A. The acceleration due to gravity, already I told you, that is A is equal to plus G. At point A, it has some height from the ground surface. So height is there. And the potential energy is also there because of height. So potential energy, already I told you, U is equal to mgh. Correct? U is equal to mgh. But there is no velocity, that is initial velocity. So U is equal to 0. So once U is equal to 0, you may think about kinetic energy, that is half mv square. Here V also called as U because of in terms of initial, you can put U. But U already is 0. So 0 into anything 0. That means no kinetic energy is there. Only potential energy. Already I told you. That is in the top position, one object or ball or stone only has potential energy. There is no kinetic energy. Okay. So in that case, total energy, which is equal to, already we saw that kinetic energy and potential energy. But here at position A, there is no kinetic energy. So I can put 0 and the potential energy mgh. It's clear? So this is a total energy is there at position A. Okay. And then at position B, we can calculate kinetic energy, potential energy at position B. At B, in the middle of that path, the body travels a displacement from A to B, that is displacement x, and reaches the point B. And the heights, what is the heights? If one object is there here, what is the height from the surface? H minus x. Yes. So here height is h minus x. So let me put PE, that is potential energy. Formula is there, mgh, but we have to change h into h minus x because of these heights. Mg h minus x. So we multiply mg into h, mg into minus x. So mg h minus mg x. This is the potential energy of that object in that position B. Okay. In that position, velocity, we have to find what is the velocity, because in that A position, object has 0 initial velocity. But here, object has some little more velocity. Yeah. So I can put something. I don't know what value, but we can put one label as VB or VC, some other thing. Okay. We don't put one value, that is 5, 10. Okay. Just label as VB or some other letter. U is equal to 0. V is equal to VB. A is equal to as well as plus G. In your 9th class, you may study that equation of motion. Yes. That is formula V square minus U square, which is equal to 2AS. You can remember equation of motion. Okay. In that case, I can put for this case. So V is equal to VB is there. So VB. U, that is mean initial velocity, but here object already in the motion. So there is no initial velocity. That is already U is equal to 0. So U is equal to 0. 2 A means H. Okay. H, sorry, G. A is equal to G. So 2 into G. S means displacement. At B, object has a displacement X because of that position. A is the topmost layer and B is the middle layer. Once ball from top layer to the reach the middle layer, it travels a displacement X. Okay. Then S is replaced by X. So we can neglect 0. So VB square is equal to 2gx. This is a velocity. But I have to find kinetic energy. Once you know velocity, then only you can find kinetic energy. So kinetic energy, we can place kinetic energy, that is half mv square. So in this position, V is replaced by VB. This is a mass. Okay, half m VB. You can recall that what is the value or what is the equation for VB square? That is 2gx. Yeah, right. 2gx. You can cancel out 2. So you got mgx. That is a kinetic energy in that position B. So now you have potential energy and kinetic energy. Now we can calculate total mechanic energy in that point B at B. Okay, so that only I can put B here, which is equal to potential energy at B, kinetic energy at B, which is equal to total mechanic energy at position B. Okay, thank you. So potential energy, what is the equation or what is the value potential energy here? Because that is, sorry, mgx mgh minus mgx. This is a potential energy. And now I can put kinetic energy, that is mgx. Yeah, clear? Okay. So now you can cancel out plus and minus because the same quantity is there. You can see mgx, but sign different. That is plus minus. So you can cancel out. So you get only mgh. That is potential energy. Total mechanical energy is there. Potential energy only is there. mgh. Okay. Now we have to find total energy at C, at point C. Okay. So let me calculate what is the kinetic energy is there, what is the potential is there. Okay. So here the body already touched the ground or hits the ground at C. So there is no height. Yeah. H is equal to 0. And after that, potential energy is there, mgh, but height is 0. So there is no potential energy because there is no height here. So ball has no potential energy. Okay, this is the potential energy 0. So now we have to find the velocity. And then after that, we have to find kinetic energy. Okay. So at C, what are the quantities there? Yes, which is nothing but displacement. Here, displacement means object travels from here to here. So object displaced x distance. So x. Initial velocity 0. Final velocity we can label as vc. And a is nothing but plus g. Okay, clear? So now we have to find that is using equation of motion. Already I told you I can write here, that is v square minus u square equal to 2as. Okay, clear? Which is nothing but equation of motion. From the equation of motion, I can write here. So you can put that what are the values you got. So v is equal to vc. So vc. U is 0. So I can put 0 here. And 2a, yes. A is replaced by g. And s is replaced by x, h, because of object travels that distance. So h. Clear? So vc square, I can remove 0. So vc square is equal to 2gh, which is the velocity of the object at position C. Then we are going to find kinetic energy. Already we are know that mv square. So here I can label it as vc square. So vc square is nothing but 2gh. So I can put 2gh for the calculation of kinetic energy at the object of at the position C. Okay, of the object at the position C. So you can cancel out 2. So here kinetic energy is equal to mgh. Yeah, clear? So here also Object has kinetic energy, but here also you can find what is the value of kinetic energy, mgh, which is nothing but potential energy. So now you can understand that potential energy is converted to kinetic energy. From these equations, you can clear about what are the total energy at the three position. Let me summarize. At A, okay, at A, total energy. I can only write total energy. Total energy is nothing but mgh. We got. At B, total energy is which is equal to mgh, and at final position, that is C, total energy mgh. You can say that it is a kinetic energy, it is a potential energy, which is a summation of kinetic energy, potential energy, whatever else, but you got the total energy is same from this equation. We can see here that it is clear that total energy is always constant. From three position, we can study that mgh is constant overall in that three position. So hence law of conservation of energy proved. Okay, clear? Okay. Let me show you one simulation according to this conservation energy. One second. So you can see one simulation, that is energy skate park. Yeah, we are going to doing one simulation, that is excellent simulation from FET interactive simulation. That simulation is entitled energy skate park basics. In this simulation, we are going to start out that by saying no friction. Okay, so no friction. I can choose from here. You can see one person is standing there, scatter. There is no friction. So friction, you can say, you can see here, friction is none. So 0. Okay. So therefore, energy is conserved. So the total mechanical energy of the scatter at any one point on the scattering track is equal to total mechanical energy at any other point in the track. So here or here or here. So whatever position, total mechanical energy is always conserved. Okay. So let me show you that first of all, I can select speed and pie chart. Pie chart, which is nothing usage. Okay. Okay. You can see that the energy graph, which is most important, because this is a relation between the object position and the energy level. Okay. So we are going to use this type of situation, and we going to keep the mass is there. Okay, we don't change mass. Mass is now 60 kg. One normal person weights, and friction is 0. We start off the friction at 0. We will later we can add friction. Okay, right. So in this energy graph, which is most important because it relates the kinetic and the potential energy and as well as thermal energy to the total amount of energy. Thermal energy is nothing but heat energy. Okay. So when the scatter standing here, no height, the scatter is not moving, and therefore no kinetic energy and no potential energy, no total energy. Okay, that is energy of the scatter is 0. But you can see if I begin to raise the objects, that person here also, once again. Okay, you can see the potential graph rises and as well as total energy rises because height increases. The scatter has some height. Now at the very top position here, the scatter have a maximum potential energy. There is no kinetic energy. Clear? So once the scatter moves down, the speed increases. Once hit the bottom, the speed is maximum. So the kinetic energy only is there. That is kinetic energy maximum. So kinetic energy, potential energy is 0. So kinetic plus potential, total energy. So total energy is there. Once I start that simulation. So now that position, you can, in this position, yes. In this position, you can see that the kinetic energy, which is equal to potential energy. Already, we already do it that calculation. Yes. So here you can say that that object, that person has some like 50% of kinetic energy and 50% of potential energy. That only the total energy is always constant. Once raise the track, kinetic energy decreases because speed decreases. You can see also speedometer, speed decreases. Yes. So kinetic energy decreases, potential energy increases. But total energy does not change at any one point. You can do the more and more, but any one point you cannot see the total energy is changing, fluctuation. Okay. So here, so the person falls down, potential energy decreases because height decreases. Yeah. So speed increases, kinetic energy increases. Once the person hits the bottom or ground level, only is kinetic energy is there, potential energy is 0. In the case of no friction, okay? So now you can recall that in the topmost layer or topmost place, that object, stone or ball or person, whatever else, that object going to have only potential energy. And once a object hits the ground, only he has kinetic energy. But this kinetic energy comes from where? From potential energy. Potential energy converted into kinetic energy. Yeah, correct. And kinetic energy converted into potential energy. So energy transformed, which is changing their name, but energy is there. Okay, energy is there. That is total energy we can see. Okay. In that case, some student may think that is uh, what would happen if some friction is there adds there. So I can friction. I can add some friction. You can see. So friction. So friction. So just to increase by two or 3 points. Okay. Friction is added once. So now you can see what would happen. Let me uh, raise that object. Okay. In the topmost layer. So you can see now thermal energy increases. Yeah, because of due to friction. Friction is nothing but restriction, surface restriction. So once you rub that surfaces, you can feel some warmer, hotter. That thermal energy. That means thermal energy. Thermal means heat energy. So here you can watch that thermal energy increases. Thermal energy, which is equal to total energy. So already it is a conservation of energy, though, because there is no kinetic energy, there is no potential energy. Where this thermal energy comes from? Because from the kinetic and potential energy. Once you add the friction, you will get thermal energy, but that thermal energy also comes from kinetic and potential energy, and in that case also conservation of law of conservation of energy is obeyed, is valid. Okay, it is clear. This is the law of conservation of energy. Okay, right. Now we are going to the another topic, that is work energy theorem. Work energy theorem, which is the most important topic. Yeah, already we know that what do you mean by work? Yes, work is nothing but it is like you have put some force on one object. That object moves some places. Then you can call it work done. Yes, yeah, work done. Some work done. Yeah, correct. So the product of force and displacement, it is called work done. Okay, that displacement means the magnitude value of displacement. So W, which is work symbol, W is equal to product of force and displacement. The dot means dot product. Okay, so force vector quantity, displacement another vector quantity. So here scalar product or dot product, F dot S. You can expand, that is Fs cos theta, which is the value, which is the magnitude of that work done. Okay. So here also we can recall that kinetic energy. Kinetic energy. Half mv square, which is a kinetic energy. Okay. Then what is the statement for this? What do you mean by work energy theorem? That means work energy theorem means the change in kinetic energy which is equals to the work done by the net force. Why are you saying net force, sir? You can say that because once this is a surface that is earth surface, the ball goes here. You can say, sir, I can push here. So, okay, that object goes here. But we say that only one force is there. But we don't know what are the other forces there. Maybe friction force, gravitational force, some other viscous force, a lot of forces there. But we can say only one force. Okay. So that's why I can say that net force. Okay. So work energy theorem, it should be dot product rather than products, because force is a vector quantity, displacement is a vector quantity, and between two vector quantity there is a scalar product, and you got scalar result. Okay, work is not a vector quantity, it is scalar quantity. That only we can add one vector and another one vector by dot product or scalar product. But you may think, why are you theta's there, sir? You can say, because in that case, suppose one surface is there, one object is there, I can push or pull. Yes, yeah, because force is nothing but just push or pull. But in that case, we don't have any theta value. But once you push or pull object from here or from this scene, okay, now you got theta. This is one of the cases, yeah, that only some books put theta, because of in that case we can include all the cases, okay. But in that work energy theorem, we are not going to into the deep into that is what is a theta and why are what is the value of theta, because it is belongs to work only. But but we are here so calculate work energy theorem, that only I can put W is equal to F dot S vector product, and here scalar product, that is a dot product. You got why are you theta's here, sir, and what is the value of theta? Theta is nothing but it is a angle between force and displacement. Okay, which is a angle between force and displacement. You can push one object in a respective angle, that is maybe theta may be 30 degree or 45 degree, whatever else. Okay, we cannot say only one angle is there. Okay, we can put whatever angles there, theta 90 degree, 45 degree, but in respective angle, that value of work is changing. Okay, for the theta is the 30, work is something. For the 45, theta is equal to 45, work is something. And mainly in the theta is equal to 90, work is something. Work is something changing. Okay, right? So that only the role of theta is there. Okay. So work energy theorem means change of kinetic energy. That is, I can put del. So del means change. K means kinetic energy. So change of kinetic energy, which is equal to work done, which is the statement of work energy theorem. Change of kinetic energy is equal to the work done by the force. Okay. But what do you mean, sir, a change in kinetic energy? Because one object is there. It has some kinetic energy. It may be some energy. I can label it initial kinetic energy. Yeah. Once ball travels some distance because of this force, I can push or pull. That only object moves from here to here. Yeah. So force I can push or pull. So object travels some distance from here to here. Okay. So once ball travels, once ball going, it has velocity. Already I told you in that conservation energy, and I showed that in the simulation. Yeah. Once balls move, its velocity increasing. So velocity increasing means kinetic energy also increasing. Yeah. So in that position, there will be another kinetic energy for that object, that same object. These are the same objects, but object is here. Here it has a kinetic energy, some kinetic energy. After some time, it travels this distance, and in this position, it has kinetic energy, something changing, something different from this. Okay, because of velocity increasing. That one, that's why I can write del K, because changing kinetic energy. So changing kinetic energy, which is equal to work done. Yeah. So let take one particle or object. mass m, it has velocity v or u. So first of all, we can write u because initial velocity. After that, it attain a final velocity v under the action of force. Okay, ma? Okay. Once object travels from this velocity to this velocity, acceleration is there. That means acceleration. Once again, one student asked that if I can't write. Once again, if kinetic energy is increased, the velocity of the object is not, sir. If one object, that means if one object, you can say it has some other kinetic energy from that initial kinetic energy, you can call it velocity increasing. One case, another one case, it mass increases. Okay, you can because in that kinetic energy formula, half mv square. M means mass of the object, v means velocity of the object. But mass of the object does not change. Yeah. In the universe, because you have one mass from Earth, you can that same mass in the Sun or Jupiter, but velocity increases. Once you told one object has different kinetic energy from the initial kinetic energy, you can surely tell that object velocity increases or object speed up. Yeah, you can say. And reverse case also valid. Once kinetic energy, changing kinetic energy decreases, you can say that object slow down. That object moving slower manner. Yeah, that velocity goes down. So in that case, kinetic energy decreases. So velocity increases, kinetic energy increases. Velocity decreases, kinetic energy decreases. Yeah, okay. So in that case, F, M, U, V, A, already I told you. We can recall that is equation of motion. So here v square is equal to v square minus u square equal to 2as. Multiplying m by 2 both side. Okay. So this side, this side, this side, m by 2. M by 2. So 1 by 2 m v square. M by 2, 1 by 2 m u square equal to m by 2 into 2as. Yeah. So we can cancel out 2 into 2. So only MAS there. MAS is there. Half MV square minus half MV square equal to F, M into A into S. Already from the equation of Newton's second law of equation of motion, you can recall that F is equal to MA. So I can replace MA by F. Yeah, correct. MA by F because of Newton's second law of equation. Okay. And this in this equation, you can say that half mv square. The kinetic energy is there. Yes. What do you mean by half mv square? It is also kinetic energy because it is a velocity. We can label velocity v and u because of initial, because of final. Okay. So this is a kinetic energy. This is a kinetic energy. So minus means change, difference. So change in kinetic energy, which is equal to F dot S. Yeah, correct. So I can write now here, that is change in kinetic energy, which is equal to MAS, MA replaced by FS. So change in kinetic energy is equal to F dot S. Yeah, correct. And you can recall that. What do you mean by work done? Yeah. F dot S means work done. That is W. So change in kinetic energy, I can put a symbol, this del. Okay. Del Ke is equal to W. That means changing kinetic energy is equal to W. Work done by the force, which is equal to change in kinetic energy. So from this equation, you can learn that is, if you push one object from one position to another position, you would change that kinetic energy. Okay, that object will change from one position to another position by the one force. By means force, you have done some work done on that object. So suppose if you work done on the object, you have done also, that is, its kinetic energy changes. Its kinetic energy also changes. Okay, clear? So this is a work energy theorem. Okay, work energy theorem. Work is nothing but change in kinetic energy. That means if you just you can say, you can see that one object, but this object is stationary or rest here. Once I push that object from here to here, speed of, okay, actually I have put some force on that object because I have to move one position to another position. Yeah, correct. Once I change the object position, that means I have done some work done. Okay, I have done some work done. That means also, that is, once object is here, it has one kinetic energy. Okay, once object goes from here to here, it has also kinetic energy, but this kinetic energy is different from this kinetic energy, from its initial kinetic energy, because velocity increases. Yeah, correct. So this is a work energy theorem. Work done on the object, which is equal to changing kinetic energy. A lot of students asking many doubts. Once again, the product of displacement, force and displacement is called work done. Yes, correct. Very good. Thanks for nice. Oh, thank you. So, which is a very simple definition for that work energy theorem. Work means products of force and displacement, because this object here, if I push force, it should be displaced from one position to another position. So force and displacement is done. Yeah, then only I can say what done. Okay, then only I can say what done. One, suppose you can say that, sir, you have put some force, sir, but that object does not move, sir, because we can stick there, or we can hold here. Okay, I can push only here, but the object does not move. What would be the work done, sir? Yes, this is one of the one case. In that case, force is there. Yeah, correct. But displacement is not there, because I can hold, I can stick here. Okay, displacement is not there. In that case, work done is 0. Yeah, correct. Yes, in that case, work done is 0, because if work is done, already I told you. So let me summarize. That is, once you say work done, you have to put some force, and that object should move from one place to another place. That only you can call it work. That work will surely change that kinetic energy, because velocity increasing. Okay, that's all. So that's all today. we can meet another one class. Okay. Jai Vidyashakti. Thank you, sir. Okay. Thank you so much. A lot of feedback. Thank you. So, okay, sir.
Thank you, sir.
Thanks.